In this section, I'm going to cover average value of a function. And so if we look at the function f over here, y equals f of x, the area underneath the curve, which is our green region here, is equal to this integral from a to b of f of x dx. So we've already talked about before how your integral is going to give you the area between the curve and the x-axis. Now, the other thing to keep in mind here is the area of a rectangle. So if I let this blue segment here represent the top of my rectangle, if I was to put the top right here, what that creates is a rectangle whose area is going to be an underestimate of the actual area between the curve and the x-axis. Now, likewise, if I was to put the top of my rectangle up here, what that does is create a rectangle whose area is an overestimate of the actual area between the curve and the x-axis. So intermediate value theorem says if this is an underestimate and this is an overestimate, then the actual area of the rectangle can represent the same value as the area between the curve and the x-axis, somewhere between here and here. So there's going to be some value or some place I can put the top of this rectangle that will create a rectangle whose area is the same as the area under the curve. And so if I place it right here, if you notice this little black section here plus this little black section here, that together should equal this area up here. If this area plus this area was to equal this area up here above the blue line, then the area of my rectangle would equal the area between the curve and the x-axis. Now this line, this blue line, is going to be the average value of f of x. That is the average value of your function. Now when I talk about an average value of something, what we are referring to is going to be the average y value on this graph. Now if we had, for example, 10 y values on your graph, you could just add them up and divide by 10. However, on a function like this, we have an infinite number of y values on here. And so we need another method besides just adding them up and dividing by how many we have, because there's an infinite number of y values. And so that's where the calculus part of this comes in. This right here represents the actual area between the curve and the x-axis. That's the green area under the curve over here. B minus A represents the base of my rectangle, and then f of x average, or the average f of x, that's the height of my blue line, which represents the height of my rectangle. So b minus a is the length of the base. This is the height of the rectangle, which means this together gives you the area of the rectangle. And the integral is the actual area between the curve and the x-axis. Now, what if we set those two things equal to each other like we have in the equation here? What we're trying to do is figure out what is the average value of f of x equal to. Well, if I'm trying to solve for this, I can move this parenthesis over to the other side by dividing, And dividing is the same as multiplying by 1 over that parenthesis. And this is how you're usually going to see it. You usually don't see it as a division problem. So this is equal to your average value of your function. This is what you're going to be implementing. This you need to make sure that you memorize. Anytime you see a number in front of your integral, you want to start thinking, is this an average value situation? And your denominator would be the upper limit of integration minus the lower limit of integration. So what this becomes is the average value of whatever this function happens to be. If this is the integral of velocity, then this would be the average velocity over this time period. All right, so let's look at some examples here. In this problem, we're asking what is the average value of the function x squared plus 1 on the interval from 1 to 3. All right, so if we take this blue line once again and let it represent the top of the rectangle, if we place the top of the rectangle here, that is definitely going to be an underestimate of the actual area between the curve and the x-axis, which is our pink area. If I was to move the top of my rectangle all the way up here, that would give me an overestimate of the area between the curve and the x-axis. So I need my rectangle to be located somewhere in between. And it would probably be located, somewhere around here, I'm guessing. It looks like about right. And what we're looking for is this area here, this pink area. If that area is equal to this area, then the area of this rectangle would be the same area as the area under the curve. All right, so if this area is equal to this area right here, and so that actually will be equal at some value. Again, because when the top of the rectangle was here, that was an underestimate. Over here was an overestimate. And so if this is an under and an over, then somewhere in between has to be the exact area between the curve and the x-axis. So I'm just putting it right here. All right, so let's actually calculate the area. And so what we're looking at is going to be 1 over b minus a, so this is 3 minus 1, times the integral from 1 to 3 of x squared plus 1 dx. So we end up with 1/2, and the integral is going to be x cubed over 3 plus x, and we're going to evaluate that integral between 1 and 3. All right, so what we end up now with is going to be 3 cubed over 3, which is 9, plus 3, minus, and then we'll plug in the 1, which is 1/3, plus 1. All right, so that's going to give us 1/2. We have a 9, a 3, and we have a -1. So that's going to be 12 minus 1 is 11. And then 11 minus 1/3 will be 10 and 2/3. All right, well, 10 and 2/3 is 32 over 3, which is equal to 16 over 3, or in other words, 5 and 1/3. And if you'll notice where we place this blue line, notice the scale of my y-axis. This is going by 2s. So this is 2, 4, 6. And we're a little bit over halfway between 4 and 6 where we thought the area would be. And so that is pretty accurate right there. All right, let's do another one here. just to once again get a visual for this, we're going to be placing this blue line somewhere to give us a rectangle whose area of the rectangle equals the area between the curve and the x-axis. So if I place the top of the rectangle here, that area of the rectangle will be an underestimate. If I place it up here, that will generate an overestimate, which means it's going to have to be somewhere in between. So if I just place it, about right here or so. Now, ideally, once again, what we're looking for is this area right here and this little area right here to total up to equal this missing area in here. When that happens, the area of our rectangle here will equal the area of the curve. And so we're going to find out the placement of this rectangle by doing our integral. All right, so what we're going to start out with will be 1 over b minus a, so that's going to be 1 minus negative 2 times the integral from negative 2 to 1 of 1/2 x cubed plus x squared plus 1 dx. All right, so we're going to end up with 1/3 here. This will be 1/2 times x to the 4th over 4 plus x cubed over 3 plus x, and we're going to be evaluating this between negative 2 and 1. I'm going to go ahead and distribute this 1/3 and simplify this a little bit. 1/3 times 1/2 times 1/4 will give you x to the 4th over 24. 1/3 times 1/3 will give you x cubed over 9, and then x over 3. And we're evaluating this between negative 2 and 1. So we're going to plug in a 1, which will give you 1 over 24 plus 1 over 9 plus 1 over 3 minus, and then we're going to put in the negative 2, which will give you 16 over 24. That reduces to 2/3 minus an 8/9 minus 2/3. All right, so if we do some combining of like terms, we have 1 over 24 minus, and this was 16 over 24, so 1 over 24 minus 16 over 24 would give us a negative 15 over 24. We have a 1/9 minus negative 8/9. That's going to give us plus 8/9, which is 1. And then we have 1/9 minus negative 2/3, which also is 1. All right, so what we end up with then is going to be 2 minus 15 over 24, which is 1 and 9/24, which does reduce to 1 and 3/8. And so you can see from the picture over here, here's 1, here's 2, this is around 1 and 3/8. All right, so now looking at the word problem here, we're going to be applying some things that we've already learned in the past. So the first thing says here is the rate of fuel consumption in gallons per minute recorded during an airplane flight is given by a twice differentiable and strictly increasing function r of time t. The graph of r and a table of selected values of r of t between 0 and 90 minutes are shown above. So we're going to be approximating the integral using a left Riemann sum. All right, so approximating the integral for a left Riemann, you're going to have base times height plus base times height plus base times height plus base times height plus base times height. We got 5 of these rectangles. All right, so the first base is from 0 to 30, so that's going to be a 30. The next base is going to be from 30 to 40, that's a 10. And then from 40 to 50 is 10. From 50 to 70 is 20. And from 70 to 90 is also 20. Now for a left Riemann, we're using the left side to determine the height of each rectangle. So the first rectangle will be determined by 20. The next one is by the y value of 30. And then 40, 55, and 65. The 70 is going to be left off on this. All right, and I'm not going to do the arithmetic, but you could add all these things up and that would give you the area. Now, is this numerical approximation less than the value of this integral? Remember, the integral gives you the exact area between the curve and the x-axis, whereas this Riemann sum is an approximation. Anytime you have a left Riemann sum of an increasing function, you are going to have an underestimate of the actual area. If I was to draw this out, you have the left side of your rectangle here, the right side here, and the left Riemann comes from here across. So you can see that you're going to have all these sections here that are actually part of the area between the curve and the x-axis, but they're not being calculated into the area of your Riemann sum. So you're going to have an underestimate because this is a left Riemann sum on a increasing function. And it must include both of those things in order to be a good justification. Left Riemann sum on an increasing function. So the next part here says for b between 0 and 90, explain the meaning of this integral in terms of fuel consumption for the plane. So I want to think about this in terms of our units. So R of t right here is measured in gallons per minute. dt means delta t, which is change in time. Your time is measured in minutes. So what we have is R of t, gallons per minute, times minutes. Now that means that your minutes are going to cancel out. That is going to leave you with gallons. All right, so you need to explain what this integral represents in terms of this problem, knowing that the unit for your answer is going to be in gallons. Integrals give you a change in something. So what this is going to be the change in the number of gallons of fuel consumed between t equals 0 minutes and t equals b minutes. So the next thing we're going to be explaining is the meaning of this right here. Now, the integral part is representing the same thing. This is your number of gallons. Now 1 over b. Remember, your b value is your time. So what we have are gallons per minute times the minutes. So that's R of t. And then this is dt. Now that gets multiplied by 1 over minutes. That's the 1 over, that's the 1 over b part of our integral. Now if you look at canceling your units, these minutes are going to cancel, which gave us gallons for the integral, but now we have gallons over minutes once again. So this integral, your denominator down here represents the upper limit minus the lower limit. So this is your average value of this function. This function is the number of gallons per minute. This is your rate of consumption of fuel. So what this integral is describing is the average rate of consumption of fuel for the plane between t equals 0 and t equals b minutes. All right, so we're going to talk through this next one here. We're not going to work the entire problem, just kind of talk through some different points here. The first thing is a test plane flies in a straight line with positive velocity v of t in miles per minute at time t minutes, where v is a differentiable function of t between 0 and 40. It says use a midpoint Riemann sum with 4 subintervals of equal length and values from the table to approximate this. All right, so to do 4 subintervals that are equal in length, your first subinterval is going to skip, and then we're going to skip another one, skip one, and skip another one. That generates your 4 subdivisions. The base of your rectangle will be the distance from 0 to 10. So your base is 10, and that is true on all the bases of your rectangle. So you're going to have 10 for your base. Now the height of your first rectangle is a midpoint Riemann, which means we look at the middle number in this interval. So the 9.2 is the height of the first rectangle. 7 is the height of the second rectangle. 2.4 and 4.3 are the heights of the other 2 rectangles. Now it says, using correct units, explain the meaning of the integral of v of t in terms of the plane's flight. All right, so remember that the integral of velocity is going to give you position. But then we evaluate that position between 0 and 40 because we're doing an integral from 0 to 40. What that means then is that your integral is going to equal actually x of 40 minus x of 0. Now, interpreting this now, this is your position at 40 minutes minus your position at 0 minutes. So if you take your ending position minus your starting position, what that gives you is displacement, or in other words, change in position. All right, so this is the change in position of the airplane between t equals 0, and this is a change in position in miles from t equals 0 minutes to t equals 40 minutes. Now, because the plane is flying in only one direction, this is not only displacement or change in position, but this is also the distance traveled in miles by the airplane between t equals 0 and t equals 40 minutes. Now, we are only able to say that because the velocity is always positive and it's always you're increasing. You're going to the right. You're going in one direction only. If you're in a situation where your velocity could also be negative, then this would not give you the distance traveled. This would just give you your change in position. That's why we really prefer to say the integral of velocity gives you the change in position, not necessarily the distance traveled. All right, so the next problem here, this is our function. This is used to model the velocity of the plane in miles per minute. According to this model, what is the acceleration of the plane at t equals 23? Acceleration is the derivative of velocity, and this is the velocity here. And so all you gotta do is take the derivative and plug in 23. This is actually a calculator question, and there is a calculator function that allows you to be able to calculate a derivative at a point. I'm not going to go through that right now, but you can ask your teacher about how to plug that into your calculator. So on part D, it says, according to the model given here, what is the average velocity of the plane in miles per minute over this time interval? So average velocity. Average means it's going to be the integral from 0 to 40, and then in front of your integral you put 1 over 40 minus 0, or just 1 over 40, of our function, which is going to be f of t dt, where this is your function f of t. So the question is, what is the average velocity of the plane in miles per minute over this time interval? This is going to be a calculator question where you can just plug this integral into your calculator and evaluate that integral.